So thank you all for coming. I apologize that I can't be there with you. I am coming to you live from COVID quarantine in Phoenix, Arizona, which is just my old house that is not currently being occupied. Um, so hopefully the voice thing won't be too much of a problem either. I am a solution architect for Carvana, and I do want to thank Carvana for allowing me to do these kind of things. They're a great place to work. But the thing you might actually know me for, the thing sometimes people remember me for, is that I'm the kind of guy that keeps a list of his favorite physicists and favorite mathematicians. And that probably tells you everything you really need to know about me, the fact that I would keep such a list. But there are one or two other things that you probably want to know about me. By the way, I do love to argue about this list. So Twitter is a very appropriate medium for telling me why I'm wrong with this list. At BS Stahl, and that's on every slide. Also, this slide deck is already available to you at amazingalgorithms.azurewebsites.net. And I could see I used the wrong version of that here, but that's all right. I do run some open source projects, so I'm an open source contributor. None of those are particularly germane to this talk, so I won't go through them, but it's here in the slide deck if you're ever interested. And one thing I will mention is that I did use Liquid Victor to build this talk. I mentioned I work for Carvana. It is an amazing place, so if you're interested in talking about working here, please let me know. And finally, I am an organizer of Arizona Give Camp, one of the founders. And if you're not familiar with the Give Camp, they're all over the country and in fact in a number of places in the world. They're harder to do lately because of COVID, but it's a weekend event where we put a bunch of software creators in a room with a bunch of great local charities and code for, the weekend, sometimes referred to a hackathon of help. And it's an amazing experience. So I encourage you to find one near you and participate. If you're interested in starting one in your area, if there isn't one, let me know and I can put you in touch with the right people. And the last thing I want to mention before I get into the real content is that this is actually my 100th public talk over the last 13 years. So you didn't know when you came here today that you were going to be part of history. So thank you all for that, because this is a lot of fun. I love doing it, and it wouldn't be possible without you guys. So thank you. All right, so let's talk about algorithms. Algorithms are fun. And when we think about algorithms, the first thing that tends to come to mind is sorting, right? And there really are two things that we really as developers do with algorithms. There's more than that with data, but there's really two primary ones: sorting and searching. Those are the two biggest things we do. And we've spent a lot of time in school talking about sorting algorithms. We do spend some time talking about searching, but there are some really, really interesting searching algorithms out there that are based on what we found in nature. So we're going to talk about some of those today. So here's our agenda. We're going to talk about two different types of searching algorithms. So we're going to talk about best path algorithms, finding the best path. And you know what I've seen best path algorithms? Obviously, it's good for mapping. I think that problem is solved. Video game developers have been using best path a lot lately to try and, to direct you. What's the best path to go from where I am to where I need to be in the game? So you see that kind of thing a lot. Then we'll look at some more traditional optimization type algorithms. Things that are used to reduce costs, whether those costs are monetary or in resources or what have you. So we'll look at a couple of really cool algorithms for doing that. And then one of the things that we do these days with these optimization algorithms is that we can use them to train AI models. So we'll look at an example of using an amoeba optimization to train an AI model. And that code is out on GitHub, and we'll look at that. Sound good? Big thumbs up? All right. Is that a sideways one there? All right, let's talk about best path. All right, so this is a visualization I put together of the process of optimizing a path using bee colony optimization. So let's set up this problem first. And I've arranged them in a circle-ish, in an oval, to make it easy to see when the best path has been found, because the obvious best path around a collection of nodes that are arranged in an oval is to go just traverse the oval, right? So when there are lines that are crossing, it's not found the best path yet. And you can actually see by the end of this simulation, there's in the bottom right there, there's still one little thing that crosses. So it didn't quite find the best path by the time I cut off the simulation. And that's always a concern with these types of algorithms, is that most of them never guarantee you optimality. So we'll have to keep that in mind. So we have 20 nodes, 20 cities you could think of, or 20 locations in a video game that need to be visited in order, or in an order. And we need to find out what's the best path through them. So what we're going to do is we're going to use bees, and we're going to simulate the foraging behavior of bees to do this. So let's start off by talking about the types of bees that are out there. We're going to use 3 different types of bees. We're going to have active workers, we're going to have scouts, and we're going to have inactive workers. And the reason I like this one, and the reason I start with this, is because it's an example of actually 2 different types of searches. We're doing both a neighborhood search here with our active workers and a random search with our scouts. And we'll see how that happens. And then we're also going to use some inactive workers to kind of converge the solution. We'll see how that works. So we'll swap in our inactive workers for active workers on a schedule. All right. For all of these, I have included a flow chart. So if you are a more visual learner, you can walk through this flow chart and use that. It's in the slide deck. I'm going to focus on talking through the pseudocode here so that you can use this. My intent with this was you could copy and paste this into a code editor as a comment, and then just start using this pseudocode in whatever language you want to implement this algorithm. Hopefully you can see this reasonably well. Basically what we're going to do is we're going to start off by initializing some number of bees. And all of these values are tweakable, of course, but I'm going to start off with 75% of them being active workers. So suppose we have 100 bees. We're going to have 75 active workers, 15 scouts. You remember that the active workers use kind of a neighborhood search, and we'll talk more about what that means. We'll have 15% of them use random search. And then we'll keep 10% aside to help converge the solution. So we start by looping through all the bees, and we're going to ignore the active workers for now. So we're just going to care about if it's the inactive. We're going to ignore the inactive. Make sure I said that clearly. We're going to start with the active and scouts. And if it's an active worker, they have a path. All the bees got initialized to a random path to start with. And we know the length of this path because that's pretty easy to calculate, right? They just go from one node to the next in their path, and we can see the length of that. What we're going to do is create a random variation in that path, change one node. Instead of going from here to here, we're going to just swap 2 of them and see if it makes it better. That's a neighborhood search. So we're just going to search the neighborhood of the current solution and see if it improves things. If it does improve things, we make that the new path for that bee. And then we check it against all the other solutions that are known so far. And if it's the best solution found so far, that bee gets to do the waggle dance. We'll talk more about what the waggle dance is in a minute, but it's something that actually bees do. It's kind of cute. Before we go there, let's talk about the scouts. Scouts have a current path, but they're going to just pick a new random path, completely random path, and see if that completely random path is better than the completely random path they had before. If it is, that becomes their new path. And they check it against all the other solutions. And if that's the best solution, they're going to do the waggle dance. So what is this waggle dance? The waggle dance is an attempt to convince the other bees. So they go to the other bees, these, in this case, the inactive workers, and they say, hey, here is where I have found the best stuff. And a large percentage of the other bees are going to say, yeah, you know what, you convinced me. And that's going to become their path. So as we swap those guys in, they're going to converge on things that have been found as the best possible solution so far. So we're going to start narrowing the focus of the search. And we're going to continue and run this loop thousands, hundreds of thousands, millions of times, however many we can, until we found a solution that's good enough. But one thing about this type of search is, since it's not exhaustive, in many cases, it would be impossible in the lifetime of the universe to check every possible solution. It means we cannot know that it has found the best possible solution. So often what we'll do is we'll look for convergence. We'll look for when have we not improved in some number of iterations, and then we can stop there. This all making sense? Interesting? Okay. All right, so colony optimization. First of all, it gives us multiple search types. So we can do both neighborhood search and random search. What I didn't mention was we just swap out when a worker bee does some number, say 100, 100 trips, then we may swap it out for an inactive worker, and then that bee goes into the inactive pot, keeping its solution. But of course, at that point, its solution could be overridden by someone doing the waggle dance. So that's where, when I say that the best known path propagates, it propagates out through that waggle dance. We have a number of things we can tweak, a number of knobs we can turn to try and get a better solution or improve our get to a quicker path to our best solution. We can tweak the number and type of bees. We can tweak the probability of persuasion. Usually start with about 90% of bees that see the waggle dance are convinced by that. But your solution may be better with more or less. And how long bees stay active. The more we swap it out, the faster it's going to converge. So all opportunities. All right. Now, so some of the features of this. This is less sensitive to scale than solutions that do, say, more exhaustive searches. Because, like I said, once you get huge, once you get to the point where you have many dimensions and many different combinations, you get a combinatorial explosion of possible solutions. This one, that doesn't matter as much. Each time it does that, it means it's less likely to find the best solution. But you're likely to find a good solution with this fairly quickly. So it's important to know your problem. If your problem requires that you have the very best solution, the methods we're talking about today are probably not the perfect solution for you. All right. So much for bees. Shall we move on to ants? ants are fun. All right. There we go. So same problem, 20 cities they need to visit, got to find the best path. And you can see this one ends even earlier with still some really non-optimal situations going on. But it is the same problem, and just we're using a different mechanism for finding the best path. So with ants, and this is actually simulating the foraging behavior of ants, the ants is ant foraging is based on pheromones, which is why it's so important that if you get ants in your house, you take care of it quickly. You lay something down so that the pheromones aren't propagated properly, too much, because ants follow pheromones, the pheromones of other ants. So the greater a path is used, the more times a path is used, the more pheromones are going to be on that path, which means that it's more likely that more ants are going to follow that path and lay down more pheromones. So that's the key. That's the principle in which we're operating here. So this can allow a solution to converge very quickly, and also can get you caught in a local minima, can get you caught in a good solution, but not the best solution very quickly. Here is our flowchart. You can see it looks a little bit simpler than the previous, and that's true. Here's our pseudocode. In this case, we're going to do some number of ants, often like 4 or 5 ants. So far fewer, far less things going on. And then each ant we're going to initialize, and they're going to look at their path. They're going to traverse their path. And as they traverse their path, they're laying down pheromones. But pheromones evaporate. So the longer a path is, the longer it takes for the ant to go to the end of that path and back. That means that a longer path is going to have less pheromone on it when that ant gets back than a shorter path would, because there's been more time for it to evaporate. So a longer path, less pheromone, a shorter path, more pheromone. So we go through, we have the ants do their work, they check their path, laying down pheromone, and then we simulate how much pheromone is left on that path. And we do so by increasing the amount of pheromone at the end of each run inversely proportionally to the length of the path, which is simulating the fact that they went out there, they came back, they took longer to do so. But we don't want to actually have that ant take longer, because we want to end each loop very quickly. So simulate by inversely I'm adding pheromone. Then each pheromone at each node, each ant, when they come to each node and the next time they traverse it, they're going to make a probability decision based on the amount of pheromone on that particular leg of the path. So if they start in a certain place and they say, okay, where can I go? I can go to 19 different nodes. Each of those paths, each of those edges has a probability of being selected based on the percentage of the total pheromone that's on those edges. So we can just sum up all the pheromone on those edges and then use a random number generator and say, we're going to go to this one based on the probabilities. So if a path has a 5% probability, of being taken, if it's got 1/20th of the pheromone on it, 5% chance, it could very well get picked, depending on the probabilities of the others. What you'll find is pretty quickly, one path gets a lot of the pheromone and starts getting picked more often. So then we can look for that convergence. And we can loop a number of times. So one thing we can do is we can reset the simulation starting from that path with maybe one ant as that path, but then random solutions for other paths. and starting again to make sure we're converging in the right place. A lot of options there. So for ants, you lay down pheromone. The amount of pheromone that remains when the ant is done is inversely proportional to the length of the path. And that amount of pheromone as a percentage of the total amount dictates the probability that a particular step will be taken at that point in the path the next time through. We can tweak a number of things here. We can tweak the number of ants. We can tweak the how much pheromone to lay out, as well as the dissipation rate of the pheromone. So if we have the ants lay down more pheromone, but also have it dissipate faster, it means the shorter paths sooner are going to get more attention earlier. If we have more time to, more CPU time to use, maybe we want to have it or dispense less so we don't build it up as quickly. We take more paths early on. All right. Again, this is not that sensitive to scale, but we do not ever get guaranteed. We don't ever get a guarantee of optimality. We go down best paths. All right, let's go on to something a little more useful, I think. More fun. We're going to talk about reducing costs. And I do want to restate that a cost can be monetary, or it could be anything you need to minimize or maximize, because you can just, maximize the inverse. When we talk about these problems, we're going to use, instead of just a 20 city map like we did in the previous, we're going to use a standard function. This is the McSwitch function. And you can see it has one big blue bulge at the bottom there. That's our point of optimality. So we're searching in 2 dimensions. We're searching in X and Y to try and find the Z point that is the best, that it minimizes our cost function, whatever that is. So we'll use this for both problems that we're about to see, both the algorithms that we're about to see. All right. So the first solution is fireflies. And I love the firefly optimization because it's so simple. This is the firefly simulation here. You can see that we started with fireflies scattered randomly about, and then they all started converging on that big red splotch in the middle. The red one is the best path that has been found to that point, and the size of it is proportional to the quality of the solution, meaning the lower that it is on that graph, the better the solution, and therefore the brighter it appears to other fireflies. Let's talk about what that means. Here's our flow chart, fairly simple. Here's our pseudocode. So all we're going to do is we're going to take a bunch of fireflies and we're going to throw them out randomly in our problem. So we're going to randomly initialize every firefly to an X and Y value. And then we're going to calculate the Z value. So what is their point in the solution? What is their the quality of their solution? And then each firefly is going to glow proportional to the quality of their solution. So the better solution a firefly has found so far, the brighter they're going to glow. And therefore, they're going to be more attractive to the other fireflies. So the other fireflies are going to start to migrate towards the brighter of the other fireflies, but not just directly towards them, because it's a percentage of all the other. I like to think about it like gravity. In fact, I use the same calculations as gravity, in directly proportional to the mass, inversely proportional to the square of the distance. Same calculation, The brighter it is, the more it's going to move towards it, but the further away it is, the less it's going to move towards it, because we want to explore a bunch of different areas. Remember, the function here has a number of local minima that we can get trapped in. So if nothing happens to explore that middle area, we could get caught in one of those local minima. So we have to be careful about that. All right. So what do? We randomly throw the fireflies out. We have each one calculate its location, calculate its brightness, and then start moving all the fireflies towards their various locations, exploring the area around them as they go. So this is a type of neighborhood search. It's searching the neighborhood around that firefly and moving them in a direction towards what we think may be the best possible solution. So we do that, we move them, we update their intensity by checking their solution, recalculate everything, and do it again. And just keep moving everything until they converge on a solution. Actually, pretty simple. Easy to work through, easy to understand. I recommend this one as a good starting point. So, fireflies uses the neighborhood search, searches the area towards the known best solution. And it uses an algorithm of the closer another firefly is and the brighter it is, the more it moves towards that firefly. Again, similar to gravity. We can tweak the number of fireflies, so we can throw lots of fireflies out there. We can tweak how fast they move towards the better solutions. And also, a real helpful one is to have a good understanding of the range of values, the range of Z values expected. Because the closer you can get to the proper range, the easier it is to define how bright a firefly should be. If we have no idea if it's just an infinite possible solution, how do you set the brightness of a firefly? How do you know how bright to make it if maximum is infinite? So ideally, we can constrain the upper bound or lower bound, the bounds of the possible solution. Now, this does work best for linear problems. If we start getting discrete problems in there where it's, if it's real values rather than integers, or if it's integers rather than real values, gosh, it does not work well for integers. Let me say it that way. Because you're forcing jumps, so we're not really exploring areas very well. Better for linear. But again, optimality is not guaranteed. And then this one is particularly bad for firefly algorithms. So this is where you really need to be careful about the firefly algorithm, is that they can suffer from sparseness problems. If I'm wanting to search the room you're in, and my cost function is I want to minimize or maximize, let's say, the density of the matter that we're searching for. We're searching for the densest matter in the room. I throw a bunch of fireflies out. As long as some of those fireflies land low in the room, they're likely to encounter, your skulls or the tables or something, and find some dense matter and maybe move towards that. But if all of them end up landing in that space between your heads and the ceilings, they're not going to find anything. It's just all going to be basically just air, and there's nothing to move towards. That kind of problem is exacerbated when we're dealing with something like space. If we're searching for the densest matter in space, well, the probability of us throwing even billions of fireflies out there and finding any matter at all is almost zero, vanishingly small. And then if you think about that with multiple dimensions solutions, we'll look at a problem here in a little while when we train our AI model that I think has 17 dimensions to it. A very common problem right now in searching words and the relationships between words has 60 dimensions to it. You add dimensions, you add sparseness, which makes it harder to find any solution at all. So this particular problem is very susceptible to that. So if you have a very sparse solution, if you don't have a lot of good solutions, good or even possible solutions, this may not be the right algorithm to use. All right, let's move on to amoebas. This one's kind of fun. So again, we're going to simulate the foraging behavior of amoebas. So hopefully you can see the simulation converging on a solution right now. And then it will restart here, and you'll see that what I've used is an amoeba with 3 points. So it forms a triangle in reality here. But this is our simulation of an amoeba. Amoebas can have as many points as we feel they need. And what they do is they converge to a solution, simulating that the foraging behavior that it's believed amoebas use. So let's look at what that is. Here's our flowchart, and here is our pseudocode. All right, so we're gonna excuse me. We're gonna create points for the amoeba as random starting points. And then we're going to calculate the foci, those starting points, calculate the solutions for those spaces. And then we're going to do this, and we're going to calculate new possible solutions. We're going to calculate 3 new possible solutions for each amoeba. The amoeba as a whole, not each point. We're going to use a contracted, a reflected, or an expanded point. And I'll show you on the next slide what that means. So 3 possible places, the 3 possible ways to move the amoeba. We see which one is better, or which of the 4 is better, the current solution or those 3 new solutions. If any of the new solutions is better, we move the amoeba to that solution. If not, the thinking is we may have surrounded the best possible solution. And so we contract the amoeba. And I'll show you how we do that. And the idea being that what we want to do is we want to surround the solution, the best solution, and then contract down to it. So here's how amoebas move. We have our 3 points of the amoeba. Those are the ones in red. We have a contracted, a reflected, and an expanded point. We start with the worst of the solutions. We take the other 2, calculate the centroid between those 2, basically the median point between those 2 solutions, and then we take the median between the worst solution and the centroid as the contracted point. We flip that over here to the reflected point, so we reflect it across the centroid to get the reflected point, and then we double that to get the expanded point. And whichever of those 3 is better, we move the worst solution to one of those 3 points. So we're always making it better to a degree, and we're always using our worst point to move. So that, what you see, you saw the simulation of it folding itself over and then eventually contracting on a solution. The idea here is this is a neighborhood search. We're going to start with random locations, explore that neighborhood as we just showed, surround the solution and contract to it. So we can change the size of the amoeba. And my heuristic for what size to use for an amoeba, Sorry about that. My heuristic for that is I use one more than the number of search dimensions. So in our problem with the Mikhailovich function, we're searching 2 dimensions, and then we're calculating that 3rd dimension. So I use 3 points on the amoeba so that we can surround the solution. If you think about a 2-dimensional solution, actually, it would be a 1-dimensional solution, I guess, where if we have a line, and we're trying to find a point, the best point on the line, we'd need 2 points to surround it and then contract to it. So a 1-dimensional solution, I have 2 points on the amoeba. At least that's what I start with. Make sense? And of course, we can also change the number of executions. We might want to do something that handles local minima. So maybe we restart it again once it contracts on a solution. We restart it in a different place and see if we get a different solution. And again, as in all of these solutions, optimality is not guaranteed. And also the same problem here with sparseness. You know, if we threw an amoeba out into the room, is there a chance that it's got some matter enclosed in it versus throwing it out in space or in multiple dimensions or whatnot? All right. So all that's great. What can we do with it? Well, to start off, the what, let's talk about a simpler problem first. This is obviously linear data. Let's say this is a graph of time. So time versus distance, maybe a train going from one station to another. And we want to use the time to predict where the train is at a particular moment from one station to the next. And you can see there's some variation in the data, errors, variations from one execution to another, those kinds of things. Now, with linear data there, like this, there are equations that we can use that will give us exact thing. Hell, you can plug this into Excel and it'll do a linear regression for you. But we're not going to do that because we're going to illustrate a point. We're going to do a linear regression using a machine learning type model, graphical model. Okay, so we're going to have one input in this, that's X, and we want to use that location to predict time to predict the location. Okay. So here's our model. It's a simple model. It has 2 nodes, an input node and an output node. You can't see my cursor, can you? An input node, an output node. And there's one edge between them. And in these types of models, any calculated node has a bias called B, and each edge has a weight, which I've called M for a very specific reason. That is, if we were to have our input X, what we need to find is the value for M and B that gives us the proper output. And if you look at that equation, the way that is calculated in all these in these kinds of graphs, we multiply the value on the input by the weight, sum that all up in here, which there's only one, so we don't have to worry about summing anything, and then apply the bias, so add the bias to it. And what we get is an equation, y, the value of our output, is equal to m times x, which is our input, plus b. And hopefully you recall from, what is that, high school algebra? That y equals mx plus b is the equation for a slope of a line, or for an equation for a line, where m is the slope and b is the bias. So we need to find the values of m and b that minimize the total error. So what is that? Well, here's our error function for this. As we change, so the, x-axis here is actually M, and this is B, and then this is our error in vertical. As we change M, what we're doing is we're changing the slope of the line. So as our slope is very wrong, our error is very high. As we get closer and closer to the slope, we come down to the bottom of that first V. And if you look closely, you can actually see there's a little bit of an indentation in there where it gets really close, but not quite right. That's showing either side of the line, where slope is close on both sides of it. Then, once we get the slope like we want it, we have to adjust the bias, adjust the intercept. And so I know it's really hard to see on this graph, but there's actually a little bit of a V inside that trough there at the bottom. And that's, going back and forth. That's where the bias matches best and minimizes the error, gives us the smallest value for our error. What we've just done is trained that machine learning model. We found the values of M and B that minimize the error. So now we can use that model to do that prediction. Plug any value for X in there, we're going to get the best possible output for the location for Y. That same principle applies to a model of any complexity. So in this case, there is a standard NIST problem, standard data set that deals with old school congressional voting. Back in the day, before you could identify the party of a Congress critter before, without, trivially, now it's easy because they're all 99% party line, right? So, but there was a time where that wasn't true. And so this attempts to predict the party of a voter, of a congressperson, based on the value of certain votes. So you can see there's 16 inputs here. We've got 16 different votes that we can work from. And the value for their vote goes in these purplish nodes here. Each one has a weight, and then the output has a bias. So we need to calculate these 17 points. So we have 17 dimensions to this problem. The other thing I said, so the value of P is the sum of all those weights times the values plus the bias. And then I put an activation around it. Let's talk about activation functions for a minute. We're trying to predict the party. So it's binary, right? It's either Democrat or Republican. Because this is America and we only have a two-party system. An activation function makes it easier for us to make a determination, because what it does is it basically trims it down to 0 or a value between 0 and 1. So it makes it kind of a probability. So the higher the value is, the closer it's going to be to 1. The lower the value is, it approaches 0. So the closer we are to 1, the more likely we are to be one party or the other. Same thing to 0. If we're right in the middle, we don't know. Okay? Now, it doesn't matter which party is 0 or which party is 1, as long as we're consistent when we're training it. So let's look at how we do that. Hopefully we can see it. All right, so I'm going to just go to github.com/Stahl/AI demos. And if we go into these demos here, you can see there's a voting amoebas project. I can make this bigger, I think. Go. And we've got two projects in here, voting data and amoeba common. I have these open at the moment in the studio. Pop that up, and there's the projects. Let's see if I can zoom this on Zoom. Doesn't look like Zoom's going to let me zoom. Nope. All right. So you probably won't be able to see this area this well. There's two projects in here. One is voting data, and the other is the common stuff. So the common stuff is about amoeba optimization. So you could use this amoeba common library to optimize your own problem. So it's out there if you want to use it. This voting data, that's the actual problem we're dealing with here. So let's go into the program CS. And we'll see that we have, I've set it to 250 executions. We load the voting data from a repository, so we get a collection of voters and their data. Initialize a bunch of statistics, results, highest accuracy, et cetera. And then split it into a training set and a test set. So we're going to use our training set to train the thing, and then we're going to test them and see how well we did with the other 25% of voters. And then we start our loop. So in each execution, we're going to train and test the model. Figure out what our best values are, calculate our results, and then just at the very end here, I run 100% of the model through it just to see the results on all of it. Let's look at this train and test model. So here's where we train it. Here's where we test it. I have got an extraneous character in there. And then we calculate some more statistics and return that information. So what does it mean to train the model? All right. Now we're starting to set up our amoeba. So we go into we create a simulation configuration object and configure our amoeba settings. Number of dimensions, size, number of epochs, and then a bunch of little tweaks around the amoeba itself that I'm not going to go into today, but you'll want to play with. And then we define the objective function. So this objective function is just a func that takes an array of doubles, that's our votes, and returns a single double value, that's our result from that, putting it through the model, results of our objective. So we could actually look at what we define it here. Let's just peek on that one so we can come back to here. Why didn't it peek that? Oh, it's doing weird things. Okay. I'm passing it in here. Interesting. I'll look for that. All right. So we're training the model. We create a new organism. This is the solver. So this is the thing that's actually going to solve the problem. And then we tell it, solve the problem and give us a solution. And then we're going to see if that's the best one. And run it, pass in the activation function as well to the model. So we're creating a new, machine, the equivalent of a trained model to send back so that they can use that model so we can use it for testing. Let's take a quick look at a model. So this is an amoeba model, or this is a machine learning model actually, where we have our bias, we have an array of weights, and then we have our activation function. So in this is where we're holding those values. So we can use those values to predict. And then it has a predict function on the model, which is actually where we apply it. So that's all that's really going to do is apply the weights and biases to the inputs and return the value and then give the result. So it figures out in this case, if it's a 1, it's a Republican. If not, it's a Democrat. So anything greater than 0.5, we're assuming Republican. This all makes sense? I realize without you getting in the code and playing with it, it's a little more, it's a little obtuse. But hopefully this code is clear enough and well commented enough that you'll be able to find what you need and get an opportunity to play with it and maybe use either Amoeba or Firefly to train your own model up. There are a lot of good data sets out there that you're going to want to play with. Hopefully there'll be a few minutes at the end here for some questions, since I'm suspecting you're going to. All right, back to the presentation. All right. So, more bio-inspired. Here's some other algorithms that we're not going to talk about today too much, but some really interesting things that we can learn from nature. And the one that I find most interesting here is the one at the bottom, genetic algorithms. I, in fact, do a couple of different talks where I talk about genetic algorithms, and one or two of them where I spend the entire time talking about genetic algorithms. That's interesting in a sort of a meta way here, because these bio-inspired algorithms all come as a result of nature implementing genetic algorithms, because genetic algorithms are just a simulation of Darwinian evolution. So what we're doing here is we're taking advantage of the 4 billion years of execution that nature has done with these species to come up with these mechanisms, right? We've had 4 billion years of evolution where the species that can best solve these problems, like how to find food, survive. And so their optimization mechanisms keep getting better and better. So we're optimizing the optimization. So we're taking advantage of that, which is a cool thing. It's also really, really good for like doing game strategy. So if you enjoy programming, trying to figure out best strategies to use for games, genetic algorithms are a really good way to do it. So what did we look at today? We looked at 2 different types of algorithms: those that help us find, minimize costs, and those that help us find best paths. For minimum cost, we just did Firefly and Amoeba, and then we used the Amoeba optimization to train that ML model. We also went through a couple of best path algorithms, B colony, and A colony. And as we said, there are a lot more out there. I highly recommend exploring them. Here are a number of resources. As I said, the slide deck is already out there. Amazingalgorithms.azurewebsites.net gets you this slide deck. And then all of these things are linked in there. One of my talks, Building AI Solutions with Google OR Tools, includes things like genetic algorithms and such. You'll want to check that out. Here's my blog. And here are a number of articles from MSDN magazine where they talked about algorithms like this, and there are a lot more in there. So I highly recommend checking those out. Finally, I showed you my AI demos GitHub repo. There's also a repo there called the algorithms, and it has many different languages, and including an entire section on C#, which I contribute to when I can. So if you're interested in seeing more algorithms and their implementations, go to the github.com/thealgorithms and check it out. And that is what I have for you today. Happy to answer any questions in the time we have left. Can I unmute the room?
Yeah, can you hear us okay, Barry?
Sort of, not well, but.
All right, does anybody have any questions for Barry? No, I think we're good here, Barry.
One on the chat.
Oh, I just lost my audio for or amoeba is movement constrained. You could, I suppose. I've never thought about it.
Can you hear me?
I'm trying to think of how you would actually do that. If you went beyond a certain point, pulling it back, it's not in the standard algorithm.
Mic check, 1, 2. Can you hear me?
Oh, wait. I think I've figured out why I can't hear you, though. Try talking again.
Can you hear me now?
Yes. Oh, very loudly now.
Sorry.
Oh, that's my fault.
Mic check, 1, 2.
Yep.
Okay. Yeah, so I know you're talking about algorithms that seem to be based on like pathfinding, and I've done, game development and other types of development for many years and using A star, and there's another, I'm not going to try to pronounce it, starts with a K that guarantees best movement. So when you were talking about Firefly and Amoeba, I'm thinking from a pathfinding perspective, if you're doing movement based off of trying to get to a desired result, that's why I was asking for the Amoeba. I was not really quite understanding what the constraint in movement is. If you're just moving to a specific point, then you're basically getting, taking averages or otherwise just kind of progressing towards the specific goal with no blockers in its place. I wasn't quite sure what, with A star and that kind of stuff, it goes around obstacles and barriers, and even with the ant thing I could see that, but I just did not understand how Amoeba could take any kind of constraints into consideration.
So if, for example, I think I see where you're going now. If there was a barrier in the way and you tried to put if one of the 3 possible solutions, for example, was in one of those barriers, what you'd end up with is not an infeasible solution. And so you wouldn't use that as the possibility there, right? So you wouldn't even be able to calculate that. So if all 3 happen to be in a barrier, for example, like in A star, like you see.
So it's like a dimensional, like a 2 or 3 dimensional space. So a line can't intersect with a barrier, or because, if a point's randomly placed, it could have the portal problem where you could check the spot, but the spot is technically free, but the line between the 2 points is not actually accessible. For example, like an island point. So you would, I guess, have to check intersection between the 2 points for obstruction.
Well, what are we talking about now? Amoebas? Because amoebas are not for best path, right? So
Yeah, I think that was my confusion. I wasn't sure. So that's not for pathing, it's more for a different,
Right.
Sorry.
These are more for optimization. So for
yeah,
finding
gotcha.
a better solution, whereas like say bee colony. So for bees, let's just use that as an example, right? If you've got a path that's a particular path that's blocked, the bees won't forage on that path. They can't, right? Same thing with ants, right? You will never get any pheromone on that path because they can't use it. So it'll just never be checked. Yeah, I don't think you'll run into problems with that. The problem with A star and those types of algorithms, anything based on Dijkstra, is that they are very susceptible, extremely susceptible to scale.
For sure,
right?
definitely.
They don't scale well. So these solutions are ones that are really good and handle scale very well. But
So very sparse systems.
and very broad systems, right? If you've got an infinite world you're trying to navigate, you're going to have a better chance of finding a path to it using one like ant colonies or something like that than you will with Dijkstra-based algorithm. Did that answer the question?
Yeah.
Well, it looks like the room's pretty empty, so I'm going to feel pretty safe. Yeah. Thank you, everybody, and have a great conference.
Thanks, Barry.